I just wanted to make a few comments on lab write-ups. I just graded a half dozen lab write-ups from the Monday lecture, and of course I've graded thousands of labs over the last 50-some years, and I just wanted to make a few comments about the labs. First of all, the purpose of these labs is to learn how to write a scientifically correct and also understandable report. And I think the audience you should shoot for is basically maybe your roommate who's a history major, or your brother or sister, big brother, little sister, whatever, and that you've done this experiment in physics lab and you're trying to explain it to them, what you did. You're not going to use words, you're going to do it in writing. So they're an intelligent person, obviously they're your brother or sister, and they have some background in science, but not much maybe. And so you've got to write your report kind of at that level. That is, you're trying to show people what you did. So you've got to describe the equipment that you used, at least briefly. Describing the meter stick is not very difficult. Describing some of the other equipment that we're going to run across this year is a little bit trickier. Sometimes you may need a picture to help describe it, and you can grab one from the write-up, or you can take a picture yourself and include it in the report, or make a sketch. In any case, you're not trying to write to me about the lab, because I've seen these labs before. I wrote these lab reports, write-ups, so I know all about them. But so don't write it for me. Don't leave out important details, and that's your kind of your audience. Let me take a look, since everybody's done this measurements lab, and I've got a few labs in front of me that I've graded, most of which are pretty good, really. And so let me make a comment about data and data handling. There's some comments. First of all, you should, in these labs, unlike a research paper in a journal, you should put down the original data. That is, in this lab, for instance, you measured the dimensions of the block. You measured the left side and the right side. You put the meter stick, you put the block against the meter stick arbitrarily. You didn't try to set the one side on 0 or 10 centimeters or whatever. So the two sides are treated equally, and they can be statistically compared, and the errors can be calculated using the laws of statistics in error analysis. So you've taken your data and you measured the left and the right positions of the ends of the block, and then you subtract those up. What you need to include, which I include in the sample table that some of you didn't get, and I apologize for that, is the first data are the left reading and the right reading. And then there's the subtraction of those readings, which is the length or width or height of the block. So start out, unlike a research presentation where you don't start out with your original data, you start out by talking about what you learned and how you learned it, and report final results and so forth, and their error. But here, put in your original data the numbers you get off the equipment, such as the meter stick or other equipment, stopwatch or whatever have you, and that's where you start, and you process those and do one example of each step in the process of leading to the answer. So that's a sample calculation, as I call it. So I've written on some of these, where are your sample calculations, and I've kind of docked the lab a little bit because there were some incomplete sample calculations. Some were there, some were not there. So simple steps that do a sample calculation of how you get from your original data to ultimately the final answer. That doesn't have to be done all at once and in the same place, but if you do a calculation, write down how you did that calculation to get the answer you got. Okay, so here are some comments that I want to make. Here's a lab in measuring the dimensions of the block, and here's one of the answers that they received for the volume, calculating that's 328.8 plus or minus 4. And I think I talked a little bit about this in an earlier discussion, but that's not quite the right answer. That is, the 4 came from multiplying the percent error for the length and the width and the height that should add up, and multiplying that by this number to get an absolute error value. So this is a value in the ones place, and so this number has to be rounded off to the ones place. What this means is this could be 4 above, it could be as 332, or it could be 324, which means the 0.8 means very little. So this is the last significant number, which is in some doubt, and it's in some doubt to the tune of plus or minus 4. So you really need to write this as 329 plus or minus 4 cubic centimeters. The digit here, or the decimal place here, so to speak, must correspond to the decimal place here. This is the ones place, this has got to be the ones place. So keep that in mind. I've seen a lot of that. Sometimes it's right, sometimes it isn't right, but these two places must correspond. They must be the units place. Okay, I've seen another example. I'll just make this up. You did your timing and you measured the length of time for 25 swings in the pendulum, and you get 38.18 or something like this. And then, the date I remember, it's 38.18, 30, and 38.16, and that's for 25 swings, and to get one swing, some people, I think, still did that. That is, they didn't use this data. They just went out, oh, you want one swing? I'll swing it back and forth once and time it. Well, the purpose of 25 swings is to cut down by a factor of 25 the error in starting and stopping the stopwatch. So if you did that, that wasn't good. So divide this by 25, and you get some number here. I think it was 1.2021, and this was 1.33. And clearly, these numbers are almost the same number. These numbers are almost 10% different. So you should notice this and say, wait a minute, I must have pushed the wrong button, entered the wrong value someplace. So I don't know which one of these is right, but clearly one of them is wrong, because these are only they only differ by 2 in the fourth significant figure, and these differ by 2 in essentially the second significant figure. So watch that. Be thinking while you're processing your data. This doesn't make sense. This is probably more like 120 or 121, if that's the right answer up there. So one of the examples was calculating the density of the wood, and this person got 519.4 plus or minus 1.9%, and that converts by multiplying this 0.019 1.9% by this number. You get 519 plus or minus 10, and that's fine. Again, any number that starts with a 1, I would carry it to one more figure, but then the error here should be to one digit. Unless this first number is a 1, then it should be 2 digits. That's generally the accepted view of that. Another comment that I had is on your conclusions. The conclusions, you'd have to distinguish between conclusions and discussion. Discussing your results is a good idea. Drawing conclusions, to me, is a little more scientifically specific, that is, numerically specific. So your conclusions should be the conclusions that are centered around your data and the values that you got, and the comparison of that data to maybe you had 2 methods of getting the same thing, maybe, such as we have in the free fall lab. We have 3 methods of getting supposedly the same thing, the value of G. So you want to do a discussion of those 3 values and how you got them and why they might be different and which one might be better and why. So forth. That would be a good discussion and conclusion. But just talking about how the lab went and so forth, that's fine, but it's not a conclusion. It's a discussion. So please keep that in mind. Now, I have a lot of things to say about graphing, and I've got some pretty good graphs, some really nice graphs, and some not so nice graphs in the 6 that I graded already, and that's kind of the typical spread. First of all, please use graphical analysis. We're going to put back on, I mistakenly took it off because I didn't think the version 4 of graphical analysis was as good as the 3.8.4 version. And it turns out that in some of the more modern Apple products, you have to use the version 4. And I'm not that familiar with version 4, but it seems, as I said to Dr. Shabbat, a little clunky to me. And maybe it isn't, just because I haven't used it. But please don't use Excel. Don't use some graphing routine you found in the calculator or used in high school that isn't graphical analysis. Use graphical analysis and get used to using it. It's a program specifically for graphing and for the analysis of graphs, and it works much better, much slicker than those other programs. So get used to that. You should have a copy of that on your home computer, and of course there's copies here. The last time I tried to show you this, the connection to the printer wasn't working right, and so we've got that fixed. And so I'd like to go through the process of putting a graph on putting a data on graphical analysis and printing it out. So let's do that. All right, so we have a graphical analysis. This is the not the front page, it's the page you get when you click on the graphical analysis icon. This comes up. Also, Logger Pro, which we'll be using later when we do interfaced experiments, has built into it graphical analysis 3.8.4. So the screen that comes up with Logger Pro, when you click on it, will be the same screen. Okay, so here are this person's data points, and here are the data down here. Notice that they're kind of scrunched in the bottom here. If I push this auto-scale button here, the big blue A, that will spread them out nicely across fill up the screen, which you want to do, fill up your graph with your data. And also you notice that there are little red circles, and you can change what the point protectors are, called point protectors, to indicate where the points are. Now, if these data are beautiful data, they're all going to fit on the theoretical straight line, and you're not going to see where the points are if they're all on the line. So that's why you have those circles there, to see how your data fit the points, fit the line. So let's go ahead to the second icon on the right, which is the linear fit, because we've linearized this by plotting period versus the square root of the length. And so we have the slope, which is 2 pi over the square root of g. You can calculate that and see how close this is to it. 2 pi over the square root of g is 2.007. So this is a little bit below that value. The data points all look pretty good on the line, but we do need to get the error in that slope, because that's the error in our experiment. And so when we plot this on graphical analysis, if you double click on this box, you will get another box that has your choice of significant figures or decimal places in your data. You can just leave it as is. Sometimes we want to go to more decimal places, so we would change this and change the number here. And we need to click the Show Uncertainty box. Okay, so that when we hit this OK button, it gives us the uncertainty in the slope and the intercept. The intercept is not critical because a zero-length pendulum should have a zero intercept, and you can see that the error here, which is 0.04, is bigger than the number here, which is 0.03 roughly, and so certainly that includes the zero. Zero is included in the range of this uncertainty and this number, so yes, it's basically zero, give or take a little bit here. So the slope here is 1.967. It should be 0.2007, and it's off by plus or minus 0.0. We'll just round that off to 0.05. Okay. So if that's rounded off to 0.05, then we would have to round this off to 1.97. So I would report a slope of 1.97 plus or minus 0.05 is my best answer. Now, that actually includes the value 2.007 or 2.01. And so, according to this analysis, we have our data includes the correct answer of 2.007 in the range of 1.97 plus 0.05 and 1.97 minus 0.05. So as far as the graph is concerned, the correct answer is included in this range of 2 pi over the square root of g plus or minus 0.05. Now, you're not quite done yet. That is, if we click any place on this graph, you can put in a title such as pendulum experiment, whatever, length versus time for pendulum, whatever you want to say, and then hit that. And also to label the x and y axis, you go over to the data and click on the x column. That's the x-axis. That's the square root of length. So down here you type in square root of length in meters to the 1/2 or something like that. And then the y column is the period. No, I'm sorry, done. I didn't do it, but I'll say it's done. In the y column, this is the period in seconds, so you type in period in units of seconds and then hit done. Then you're ready to print it out. So go to the file option and don't do the print. What this is a print screen option, which will print your data, which you already have on a table someplace. So if you push the print graph button, it will only print the graph part, which makes it nice and a little bit bigger, and it's easier to see the numbers here if it's a little bit bigger. And press OK, and the printer will print it out if you tell it. So there's the graph. We don't really need this that area there. I should have discontinued that before I printed it. But in any case, there's the graph, which you can simply staple to your report and discuss. So I didn't write all the numbers down for the data, just the first row, just to show how this goes. Again, the length in centimeters, converted to meters, and then added the radius of the bob to make it an ideal simple pendulum. A square root of that is that number there. And you use two timings. They're very close to each other. They're 0.6 seconds off. And if you divide that by 25 to get the time per period and average them, you get a 1.483, and that means that the maximum deviation is 0.009, or about 0.6%. Now, I didn't do that for the other two. If you do that for the other two, you can average all three and get a percent. Let's say the average comes out to be 0.8%. One of them is 1%, and the other one is 0.4% or something like that. Okay, so that's one error. That's the error in timing. Let's say, I'm just making this up, it's 0.8% by averaging these. The other error in this experiment is measuring the length of the string, which is tricky. You can't measure it to the nearest tenth of a millimeter because, well, you did it, and you know that you can't measure the ends very carefully. And so I'm going to estimate that I can measure the length to within 2 millimeters. That's being generous. 2 millimeters is 0.2 centimeters, and I'm going to take an average length. I didn't write all the lengths down, but I'm going to take an average length of about 50 centimeters. one was higher, one was lower, but about 50 centimeters. 50 centimeters is 500 millimeters, so 2 millimeters, 2 millimeters out of 500 millimeters is 0.4%. So I'm predicting an error based on my measurement of length and measurement of time. Oh, by the way, that's a good point. That is, this is the square root of the length column, so you have to divide this by 2 because it's the square root of the length. The uncertainty in the square root of the length is half the uncertainty in the length. That's getting a little fussy. So, so the total error I'm expecting is 0.8%. I'm just making that number up, plus 0.2%, which is about 1%. So I'm saying that if these are the error sources and nothing else is going on, this experiment should come out within 1% of the correct answer, 2 pi over the square root of g, 2.007 roughly. And so it turns out that the difference between 2.007 and 1.967 is just about 2%. So we either have underestimated our errors, which I don't think we did. I think we overestimated this error. So there's something else going on. Could be error resistance, could be something wrong with the measuring of the meter stick, systematic error of some kind, or maybe we swung it too far and it wasn't obeying that ideal equation that we talked about for swinging through small amplitudes. Anyway, we're close to the right answer, and we're within 1% between my maximum value of plus 1% above 1.967, and that's what you conclude. That is, sometimes you can't explain where all the error comes from, but hopefully you can come close. And this person came real close.